Hello, Math 126 students. This is my third attempt to record this video. My computer and internet seem to be crashing, so I'm going to keep it short. Exam 2 is next week. I just want to give I do have a video already that I've made last quarter where I work through my two most recent exams in my exam archive. But let me just say a couple specific things to this quarter. Our exam will be about chapters 14 and 15. It will not include 13.4, so there would be no acceleration. It will not include center of mass, so it won't have 15.4. So what will it have? It's going to be about surfaces and studying them. I could ask some small question about domains or level curves, but really page 1 you can expect is going to be about partial derivatives. How do you take partial derivatives? Can you do it if it's implicit? All the things you saw in the homework. Don't be surprised by any of that. I'm going to ask about a tangent plane or linearization. That's going to be page 1, somewhere on the test. You're going to have to compute second derivatives somewhere on the test. So what are the things we've done? Really what we learned was beyond some general things, if we want to study where the important features of a graph are, we find the critical points. So that requires you find the partial derivatives and set them both equal to 0. Now there's a process of solving a system of equations. It's actually not really this course, it's more of a prerequisite, but I try to give you a careful process for how to always solve a system of equations. Look to factor first if you can, and then for each case, solve for one variable in one equation and substitute into another equation. You do not set the equations equal. We've talked about that quite a bit. I still saw a lot of that. I see students make that mistake a lot. So let's not have that happen. I saw it on exam 1 when people were trying to find a point of intersection of two planes. They just set two things equal, which is the wrong idea. Anyways, we've done a lot of that. You did a lot of it in homework. You can find a lot of that in old exams. We should be able to immediately start such a problem. And then what do we do with them? Sometimes I ask you to classify them, in which case you need to compute the second derivatives, plug in, and make appropriate conclusions. I could ask you a question about an applied max and min. I guess I didn't put that here. An applied max and min question, I just want you to set up the objective, the thing you're trying to maximize, plug in the constraint. That's going to give you a two-variable function. And I want you to find the critical point and just stop and don't do anything else. Absolute max and min, I want to see the function for each boundary. Let's look at some old tests so you can see. Maybe I'll just click randomly. Let's look at the solution just so I can discuss. Oh, that's exam 1. Apologies. Exam 2, let's just pick an old one. So the first question is probably about 13.4. We're going to skip that. That's a 13.4 question. There's a question here about finding the tangent plane, so immediately start finding the partial derivatives. We don't want to be scared by those partial derivatives. Compute the partial derivatives. Plug in and done. This is a volume, so I'll talk about that in a second. This is a polar volume, so that's something we'll talk about in 15.3. This is a draw the region, which is really the skill in chapter 15. And then we have a global max and min. So what does a global max and min? I did a lot of this in class. What does the solution need? For each boundary, it needs the one variable function. The z equals 9, the z equals 4x squared minus 4x plus 9, and this. I need to see those three functions. That's how I grade this. Does the student have this function, this function, this function, and did they find the critical points of the surface itself? If those four things are there, you're going to get a lot of the points. You still have to finish it out and show me that you know in the end that the critical points for the function that are in the region, and for each boundary, the endpoints and the critical numbers for the one variable function, you need to find the z for all of those and see what's the biggest. That's a bigger process problem. Here's an applied problem. So for an applied problem, I don't ask this anymore. I don't say use the second derivative test. I would just have you get here and stop. We did that one in class. Let's look at a random other one. I don't know this one. Again, the 13.4 question, let's skip. That's all 13.4. Find and classify the critical points. Take the partial derivatives set them both equal to 0. In this case, I don't see a natural way to factor, and so then I'm going to take one equation and solve for one variable and substitute into the other equation. That's going to give me a one variable equation to solve, which I'll solve, and in this case it gave me two possibilities. And you plug that back in. In this case, in this situation there was only one case, so that you could plug it in anywhere, but it all stemmed from here. Then you classify. You take the second derivatives, you plug it in, you make appropriate conclusions. This was negative, saddle point. This was positive, and that was positive, so that means it's concave up, local minima. So that needs to be routine, that sort of question. Find the linear approximation. Okay, another one of these. Implicit, take the derivative. Be ready for that. That's coming. Here's a region. Can we describe the bounds? There's a couple different ways. Here's another region. Can we draw it and find the bounds? Here's another region. This one's polar. Can we get the bounds? That's what this exam is. Let's click on another one. Okay, again, ignore the 13.4 question. We have an implicit partial derivative problem. We have the linear approximation. We have a region. You have to reverse the bounds. So really the question is, can you go from the picture to the bounds? We have another one. Can you go from the picture to the bounds? Another one. Can you go from the polar region to the bounds? Notice there is some integration, like this one required you integrate sine squared. Integration is not going to be a major part of it, but somewhere in the test you're going to either have to do substitution or by parts or a trig integral. That will be a small part. In this case, all the integration was straightforward, but it still took some calculation. Find and classify all critical points. Take the partial derivative. This is before I used my tree method, but I basically did the same thing. Factor for. In this case, I decided to start with the second equation, so I guess I sort of made a tree. Classify. Global max and min. Notice the big things that need to happen. I need to have a one variable function above this boundary. I need to have a one variable function above the other boundary. And then I need to find the critical points I already found in the previous part. Let's keep going. Let's click on another one. I'll go a little further back. Again, ignore the 13.4 question. Okay, we have implicit differentiation. We're going to just take the derivative. Understand that z is a variable and x is a variable. Let's keep going. Okay, this is about drawing that region and then knowing how to take that region and give these bounds. Okay, this is about drawing this region and knowing how to take this region and give those bounds. This I won't ask. It's an average value question. We don't have that in the homework anymore, but ultimately it was about understanding the region and finding the appropriate bounds. It's a polar question. Global max and min. So the things that need to happen is above this side, I need to have a one variable function. And above the other side, I need to have a one variable function. Then I need to analyze those. So hopefully you're kind of getting a flavor. This exam, it's a little more straightforward what's coming. I already clicked on that one. Let's look at a more recent one. Okay, first we have to do a partial derivative. Notice you have to treat, what is it asking? For the tangent plane. That means we need to compute both partial derivatives. Notice how I plugged in right after I computed the partial derivatives to save myself some time. This is about how can you take this region and find the bounds. It's much easier to do in terms of y. The first thing I did is I labeled y, and then I labeled the graph correspondingly. You could do it in terms of x as well, but it's much messier. Find and classify the critical points. Step 1, take the partial derivatives. Look to factor first. That gave me two cases. Again, this is before I did the tree method. I've only been doing that just this last quarter. But it's still the tree. It's two possibilities. We saw it. I did compute the second derivatives. Reverse here. So this question is about taking this region and drawing the picture, and then thinking about it in terms of y instead. This question is about taking the region, drawing the picture, and figuring out the bounds here and in polar. This is a polar region. So after we talk about 15.3, we'll know how to describe the region, give the bounds. This required integrating, doing some trig integrals. That was probably the hardest integral on that test. Then we have a maximization question where it says minimize the cost. So that's step 1. You can see I wrote that down first. And then I had a constraint. I substituted in. That gave me a two variable function. and then I found the critical point and I stopped. That's how I ask things now. So there's a bunch of exams where you now are seeing, this is what I would do as a student. This would be part of my studying. So what does this look like? I needed to take the derivative of that. I needed to take the partial derivatives. In this case, I decided to solve the second one. Substitute it in, solve, find the second derivatives, classify. This one you need to draw the region, and from the region get the bounds. This one you need to draw the region, and from the region get the bounds. This one they gave you the region, and from the region you needed to know what the bounds were. It's a polar. This one required me integrating a trig, a cosine cubed. So you'd have to remember how to do cosine cubed to finish that problem. This is a global max and min. Notice that there are two boundaries. And so ultimately I would need these two functions above those boundaries. Okay, so I think that's enough. Again, hopefully this video worked. I hope that gives you. I'm not going to ask again about center mass. I just put it on here. It's kind of nice to see some other application, but that's not on our test. So you know what's coming based off of a discussion there. Finding critical, 3 things. You got to be really good with partial derivatives. 2, you got to be able to find critical points and understand the couple big applications we have with that. Applied max and min, and global max and min. Now for second derivatives, understand the process I've been talking about in class. Draw the region, and from the region can you get the bounds. Okay, hope that helps.